Hello and welcome to this webinar on how to choose the right NIR setup for your application needs. My name is Henrik Elholm and I'm head of Feed and Forage in Foss. We are a company with more than 30 years of experience with NIR in food and feed industries. And today we will share some of our extensive insights on different NIR technologies and chemometric methods and what you need to consider in relation to your specific application needs. This webinar is the first in a series of 3. Next week, we will share some very concrete examples on how one of our large customers in Southeast Asia is using network management software to standardize factory operations, and also how they use Foss Manager in doing so. And the week after, we are providing a practical overview of relevant standard operating procedures and preventive maintenance schemes to maximize the uptime of your NIR solution. Today, Jakob Ries Folkenberg will give an introduction to spectroscopy and provide an overview of different NIR technologies available. Jakob has a PhD in optics and has more than 15 years of experience with Foss, where he today is Vice President of Technology in R&D. Next, Lars Nørgaard will talk about calibration and prediction principles and discuss pros and cons of different calibration models. Lars has a PhD in chemometrics and many years of research and teaching experience within chemometrics and spectroscopy for food agri applications. Lars started in Foss 10 years ago and is today Senior Manager at R&D Data and Algorithms. And then Thomas Nielsen will provide a practical case example on the analysis of moisture in corn and how different calibration models compare and the effect of sample size on prediction performance. Thomas has a PhD in physical chemistry and has been with Foss for more than 12 years, now working as calibration specialist with particular focus on supporting large NIR networks that run on Foss technology. At the end of the webinar, we will have a Q&A session where we will answer all the questions you may have. Before we start, all participants will be muted throughout the webinar, but we encourage you to ask questions as we go along using the chat function. We will then answer the questions when we get to the Q&A session. And with that said, I would like to hand over the word to Jakob. Thank you.
Hello, my name is Jakob Folkenberg. This part of the webinar today we have called NIR technology. Here, I will talk about the physical principles of NIR spectroscopy and the instrumentation required to make the best possible measurements of feed and food samples. As part of this, I will also discuss different NIR spectrometer technologies and their advantages and disadvantages. So let's start by having a look at the basic principles of optical spectroscopy. If you shine light on a molecule, in this case it's a water molecule, there's a probability that some of the light will get absorbed and excite vibration in a molecular bond. You can detect this incident because some of the light has now disappeared. However, the absorption process only happens the wavelength or frequency of the light matches the vibrational frequency of the molecule. Since the vibrational frequencies are specific to specific bonds, this will allow us to identify the bond and thus very often also the whole molecule. Look at an example. Liquid milk and milk powder have many vibrational frequencies in different parts of the optical spectrum. They correspond to fat, protein, lactose, and water molecules. Note that the same molecules may appear several places in the spectrum corresponding to different vibration modes that have been excited. In spectroscopy, we usually split the spectrum into 2 parts. The first part shown on the right is the mid-infrared range from approximately 3 to 10 micron. And the second part is the near-infrared range shown on the left, which extends from approximately 850 nanometers to 2500 nanometers. When going towards longer wavelength, the absorptions grow stronger and stronger. In mid-infrared, we find the strongest absorptions corresponding to the so-called fundamental vibrations of the molecule. Since the absorptions grow stronger, the penetration of the light into the sample decreases, and shorter sample thicknesses can be measured. This is why we mainly use mid-infrared for liquids that can be injected into thin cuvettes, and NIR is mainly used for solids, where you want a longer penetration depth to measure a larger volume of the sample. In this webinar, we focus on the NIR applications, but no matter which part of the spectrum you use, you want the best possible use of your light in the spectrometer, which we will also dig deeper into. Into the NIR part of the spectrum, you can see that there are many possibilities for detecting a specific molecule because the molecules have both overtones and combinations of the vibrations here. This is also why the NIR region is subdivided into 3 smaller regions: the shortwave NIR, the longwave NIR, and the extended NIR. So you may ask which wavelength range to choose for your application. This depends both on the parameters you want to measure, the heterogeneity of the sample, how the sample can be accessed, and other factors that may be specific to your application. I will get back to this in the third and last part of this webinar. Now, let's have a look at the very basic elements of a whole NIR instrument that enables us to measure the molecules in a real sample. To generate the light needed for the NIR measurements, a more or less conventional light bulb is usually used. There are other technologies for generating NIR light, such as light-emitting diodes or so-called supercontinuum light sources based on fiber lasers. However, the best price-to-performance ratio is still obtained from an incandescent lamp. Next, the light must interact with the sample. There are a number of different ways of doing this, which I will come into later. But this geometry or sample presentation needs to be matched carefully to the nature of the sample and the parameters that you want to measure. After interacting with the sample, the light must be split into its different wavelength components in a spectrometer. And the light is finally measured with a detector matched to the relevant wavelength range that you want. In some cases, the spectrometer is placed before the sample, but the principle is still the same. The graph of the light level at each specific wavelength we call the raw sample spectrum. This contains information not only about the sample, but also the lamp source, the spectrometer throughput, and detector sensitivity. To eliminate the spectral features that do not originate from the sample, the spectrum from a so-called reference also needs to be measured. The reference has a well-defined and optimally flat spectrum. Finally, the absorbance spectrum can be calculated from the ratio of the raw sample and the reference spectrum. The shape of the absorbance spectrum depends now only on the sample and its composition. Using chemometric methods, the sample composition can be calculated from the absorbance spectrum, which we will come into in the next part of the webinar. Different NIR instruments often utilize different spectrometers and detector technologies. The advantages and disadvantages of this will be the topic of the next part. You may say that the spectrometer and detector system is the heart or maybe even the brain of an NIR instrument. In any case, the spectrometer, detector, and sample preparation systems together will determine the range, the quality, information content of the absorbance spectrum you acquire from a sample. When you go to conferences or read the literature on NIR spectroscopy, it may seem that there are many different NIR spectrometer technologies. So which to choose and what are the advantages and the disadvantages? In reality, there's basically only two different spectrometer principles that we will look deeper at now. The first spectrometer type is shown on the left and exemplified with a so-called monochromator. This type of spectrometer relies on a wavelength-sensitive element, in this case it's a diffraction grating, that splits the wavelength of the light into different directions. By turning the grating, you can scan the relevant wavelength over the detector and generate a spectrum. So there's a relation between the angle of the grating and the wavelength you measure, which can be accurately calibrated. On the right is shown another principle. This spectrometer is based on a device called an interferometer. An interferometer splits the light into two arms, and by varying the length of one of the arms, you can make the wavelength of the light interfere constructively or destructively on a beam splitter. The signal recorded on the detector is a so-called interferogram, and it is the variation of the light as a function of the displacement in one of the arms. When the interferogram is Fourier transformed, you get the spectrum, hence the name Fourier transform spectroscopy. A laser keeps accurately track of the displacement in the arm, and this is the reference for the wavelength or wave number calibration of the spectrum. FoSS has many years of experience with both types of spectrometers, and we have found that the optimal use of the technologies is to use Fourier transform in the mid-infrared and the monochromator-based technology in the near-infrared. I will get further back to this in the next couple of slides. There is a variant of the monochromator that should be mentioned, the so-called detector diode array. Like in the monochromator, a diffraction grating splits the wavelength of the light into different directions. But instead of turning the grating, an array of detectors are used to cover the wavelength range. So each pixel corresponds to a specific wavelength. The advantage here is that there are no moving parts, so it's ideal for applications where shocks or strong vibrations may be an issue. For instance, in a process environment or a portable solution. The limitation of the DDA at present is that it is only affordable in the shortwave NIR and the long-wave NIR regions due to the availability of cost-efficient array detector technologies. This table sums up the most important features of the different spectrometer technologies. The two first rows concerning multiplexing and throughput are important for achieving the best possible signal-to-noise ratio of the absorbance spectrum. Multiplexing allows the detector noise to be integrated for a longer time or distributed over the different wavelengths, thus increasing the signal-to-noise ratio. Historically, this is referred to as the Felget's advantage in Fourier transform spectroscopy. Throughput is a measure of how much light can enter the spectrometer, which helps to increase the signal. In monochromators, it is easily scalable with the input slit size and the grating size. In interferometers, it's generally possible to have larger input apertures, which is often referred to as Jacquinot's advantage. In DDAs, the throughput is not quite as high due to the available pixel sizes of the detector array. The multiplex and throughput advantages of Fourier transform spectroscopy are critically important when measuring liquids in the mid-infrared range of the spectrum, where light sources are weak and detectors are rather insensitive. However, Based on the experience that we have gained at FOSS over many years, we have demonstrated that in NIR it is possible to achieve the same signal-to-noise ratio for the monochromator and the FT technology, because light sources are brighter and detectors are more sensitive than in mid-infrared. It is simply other factors that determine the signal-to-noise ratio that you can ultimately achieve. We have also found that the DDA spectrometers are good enough in many applications where the highest possible performance is not required, and especially for moving samples, the technology is superior because the whole spectrum is recorded in real time. Another feature of discussed is the resolution, and the ability to vary the resolution, which is possible with a Fourier transform spectrometer. This is relevant if you need to measure many different types of samples, for instance gases, where absorption lines are narrow and closely spaced. However, in food and feed samples, we do not see these sharp features, and it is not necessary to work with variable resolution. Actually, on the contrary, if you want to have stable and transferable prediction models, you want to keep the resolution fixed. Sometimes it's also emphasized that the interferometer has a simple linear wavelength or wave number scale, whereas other spectrometer types requires a polynomial fit to calibrate the axis properly. This is true. However, the wavelength accuracy required in a feed or food application is easily achieved with a polynomial fit, and it's typically a fraction of a nanometer. Regarding the wavelength range, the monochromator type has an advantage since it's easy to extend or adjust the range by rotation of the grating and the grating design. In a Fourier transform spectrometer, however, there's a lower limit set by the laser reference, which is typically in the red part of the spectrum. This means that monochromators can easily be designed to cover the visible part of the spectrum, which is increasingly needed for feed and food analysis and quality control. Finally, the robustness should be considered. The interferometer is generically sensitive to small movements on a scale determined by the shortest wavelength you want to measure. This is another reason why Fourier transform spectroscopy is more challenging in NIR than in mid-infrared, where the wavelengths are longer. To sum up, due to the advantages described here, FOSS has chosen to base its NIR portfolio on monochromator and DDA technology because they offer the overall best performance, versatility, and robustness to our customers. As a final topic of this part of the webinar, let's just have a short look at the detector technologies relevant for NIR spectroscopy. In practical use, there are mainly 3 relevant detector materials as shown here. The main difference is the wavelength coverage, the shapes and the sizes available. Silicon detectors cover the shortwave NIR range and the color range. They're cheap, they're fast, and they're very efficient. They are available in both small and large areas and also in detector arrays for DDA spectrometers. The so-called in-gas detectors, which are alloys of indium gallium and arsenide, comes in different variants. They can cover long-wave NIR and the extended NIR range. They are not as cheap as silicon, they are affordable and very efficient. They are also available in arrays up to 1650 nanometers. Above that, the array detectors become very expensive. Finally, lead sulfide detectors will cover the same ranges, the long-wave NIR and the extended NIR. They are also affordable and very efficient, and they are available in large areas for low light level detection. Now let's have a look at different application aspects of NIR technology. Different sample types and applications require different measurement geometries or so-called sample presentation in order to achieve the best possible analytical results in the end. This final part goes through the four most common measurement geometries, their advantages and typical uses. In the end, I will also explain how high performance is maintained over time and the ability to use calibrations developed on one instrument on another instrument, the so-called transferability. One of the most common measurement geometries is so-called reflection measurements. In this case, the light illuminating the sample is incident on the same side as the spectrum is recorded. The advantage of reflection measurements is that the full NIR spectral range is accessible up to 2,500 nanometers, so it contains the maximum spectral information. The color range is also accessible. Typical applications of reflection measurements are, for instance, for compound feed, for milk powder, or for corn and grass silages. And parameters such as fat, protein, moisture, fiber, ash, and starch can be measured. One thing to pay attention to is the limited penetration depth at the long wavelength, which means that often you would need to measure a number of subsamples and generate an average in order to represent the sample the best way. Another common measurement geometry is transmission lens through solids. In this case, the illumination is incident on one side of the sample and the spectrum is recorded from the other side. The advantage of transmission measurements is that you can use shortwave NIR and get a very large penetration depth, which means that every measurement will represent a large sample volume and it's well suited for heterogeneous samples. Typical applications here are wheat, on soybeans and other grain types, which is typically measured in the Infotech instruments, or it could be meat and cheese samples measured with the FossCan. A third kind of measurement geometry is so-called lateral transmission. In lateral transmission, the sample is illuminated from one side and the spectrum is collected from the same side but offset from the illumination spot. The measurement principle requires that light is scattered inside the sample, so it's possible to propagate from the illumination point to the sample point. The advantage is that you get a large penetration depth into the sample and every measurement represents a large sample volume. And the sample can be accessed from one side, which means it is ideal for a process window looking into, for instance, a dairy process. Typical applications are butter or WPC, and parameters could be such as moisture, fat, solid non-fat, and so on. One thing to pay attention to is that lateral transmission requires a certain level of light scattering in the sample, so it will not work for clear, transparent samples without light scattering. Finally, liquid transmission measurements with NIR should also be mentioned. As explained previously in the webinar, we prefer to use mid-infrared spectroscopy for measuring liquids. However, for some liquids, there is an advantage of using NIR. This is, for instance, liquids with larger particles that it's not possible to suck into a flow system. Or it could be applications where the samples needs to be presented in disposable vials and cuvettes made of materials that are not transparent in the mid-infrared part of the spectrum. And finally, with an NIR instrument, it's easy to heat the sample to elevated temperatures for measurements. This is relevant, for instance, for fats and oils. Typical applications of liquid transmission is vegetable oils for oil crushing, and parameters could be such as acidity or iodine value. And furthermore, the color of the sample will also be accessible with liquid transmission. Now, let's go to a different topic. In addition to finding the optimal measurement geometry for your samples, you also want them to maintain the high performance over time. This is a very important application aspect and a property that may vary a lot between different spectrometer products. At Foss, we have developed very successful proven solutions to ensure high performance over time. One part of this is a so-called master concept that ensures that all instruments are linked back to the same golden spectrum when it leaves the factory. When the instrument arrives at a customer site, we make sure that the high performance is also maintained over time. This is done by using internal wavelengths and reflection standards that frequently make sure that the x-axis and the y-axis of the absorbance spectrum is correct. The stability of the spectrum that is obtained this way is demonstrated or shown in the graph on the right. If you zoom into the peak at 1467 nanometers, you see that over a long period of time, this peak is exactly at the same place in the spectrum. Of course, if you zoom into it, there are small variations, but these variations have no impact on the predictions that comes out of the instrument in the end. The performance can be monitored over time using check samples. Another very important property is transferability. This is illustrated here in a study where a calibration has been developed on a master instrument, and this calibration has been used on 5 other instruments, and the performance has been evaluated. The graph shown on the right shows that all 5 instruments have exactly the same measurement performance as the master instrument, and this is without any modifications to the model, and the model has been directly deployed. The ultimate limit of transferability is that if the performance achieved if the transferability performance achieved is better than the repeatability when repacking the sample, then the transferability basically cannot be better. So, to sum up the different topics of this webinar, we've seen that NIR spectroscopy is a very strong tool for identifying and quantifying the composition of food and feed samples, in particular solids of different heterogeneity. High performance measurements are achieved by careful optical design of the instrument, particularly emphasizing sample presentation geometry and the spectrometer technology. Monochromator-based instruments have several advantages. It's possible to have a very high throughput, thus achieving a high signal-to-noise ratio of the spectra. It's possible to have a very broad spectral range, covering even the visible part of the spectrum. The monochromator design can be made very robust, and we've seen that long-term stability may be achieved using the internal wavelengths and intensity references. Furthermore, it's possible to manufacture micrometer-based instruments that are so identical that we can achieve a transferability that is better than the repeatability obtained when repacking the sample. Finally, we've also seen that DDA-based instruments are ideal for process or portable applications where samples are moving fast or bumps or shock may occur. So this ends the first part of the webinar on NIR technology. I will now pass on the word to Lars Nørgaard, who will talk about the development of calibration models for NIR. Thank you very much.
My name is Lars Nørgaard, and I really look forward to tell you about the calibration models that we have implemented in our FossCalibrator, our analytical tool for development of applications in the food agri area with the near-infrared solutions. I will take you through a short introduction on calibration and prediction, overview of 4 methods: partial least squares regression, a modified version of it, local, and a nonlinear method based on artificial neural networks. And after that, we will have a discussion on pros and cons for the presented methods and why we have selected these methods. And we will end with a demonstration in FossCalibrator where we benchmark PLS to ANN, and this is conducted by my good colleague, Thomas Nielsen. When we talk calibration and prediction, we're normally in the situation where we have analyzed a number of samples, our calibration sample set. So we have a number of spectra, near-infrared spectra, as illustrated by this plot here. And for each of these spectra here, we have an attached reference analysis value. This could be the protein content of 15.2% protein. So we have all these values attached to each individual spectrum over here. And the whole purpose and idea of doing calibration and developing a model is that we can use this model for future use. So we only have to record the near spectra of unknown samples, add the calibration model, and then we get a prediction of the protein content. This secures that we can do this very fast. We only need the time to acquire a spectrum, which is 30 seconds or 1 minute type. Then we can submit it to the model, and then we get a prediction of protein and a lot of other components as well. So we can get multiple predictions if that is needed. So this is sort of the basics of calibration and prediction modeling. We use machine learning techniques to make these models. And machine learning techniques, this is about making good computer programs and software where we can access data and we can automatically make and develop the models. So we do this from the data. We do not present a first principles model up front, but instead we have a collected data set, and then we learn from this data set how the relation between spectra and protein reference analysis is in a given case. I have a simple example here. This is the spectrum of protein. I took it from the internet, so it's a little bit blurred here. So we have a spectrum from 750 to 2400 nanometers, and I can see it has shifted a little bit, but the peak should be here at 2180 nanometers. And one way to do classical calibration is to use a univariate linear regression. So we can analyze 10-12 samples shown here. So we can have the concentration on the x-axis and the intensity at 2180 nanometers at the y-axis. And then we utilize least squares. We utilize least squares mathematics. So we would like to minimize the least squares. And the least squares is simply the distance from the point to the line. In this case, we square this distance and then we sum it for all the data points here. And when we do that, we're going to fit the line that minimizes these distances seen over all samples. And this is called the least square solution and the linear least square solution to this equation. In the univariate case where we only analyze one wavelength, you can write the equation like this, that the protein in this case equals the slope, the regression coefficient 1, times the intensity at 2180 nanometers, plus an offset B0, plus some noise. So this is the model we want to analyze, and these are the errors that we would like to minimize by least squares. And the whole idea is to come up with an equation where we can estimate protein because we know B1 and B0, and then we just measure the intensity at a given wavelength. So we calibrate B1 and, in calibration, we estimate B1 and B0 from a sample set, and then we can use this to do predictions. So assume B1 and B0 has been estimated to 10 and 4 from a calibration set. Then we can use this equation with a new sample where we measure the intensity to 0.5 to say 10 times 0.5 is 5 plus 4 is 9% protein. This is a simple case because the world is a little bit more complex. Here you can see the protein. This light bluish curve here is the protein. But in a real biological sample, we also have starch and water and fat and oil and many, many other things. And all these other spectra here, they also give signal at 2180 nanometers. It's not only protein, so there are a lot of interference that we have to handle. And one way to handle this is using multivariate regression, utilizing all the measurements in such a spectrum, not only one, but all, for instance, 2100 measurements in such a spectrum. And this is exactly what we utilize in partial least squares regression. Before we come to that, I would like to discuss a small difference here, but an important difference between correlation and covariance. In covariance, you measure the intensity of, for instance, the spectral signal and how it co-varies with the reference analysis. So we take one wavelength here and say how does it co-vary with the reference analysis. The higher the x, the higher variation in the x, and the higher variation in the y, the higher covariance. Covariance is not necessarily the best thing to look for because large peaks that by nature have a larger variation than smaller peaks, they would tend to dominate, but they might not be relevant to the protein. So another way of looking into a model is by looking at the correlation. And in correlation, we take the covariance and divide by the standard deviation of the spectral variable and the standard variation of the y variable. And down to the right here, I have plotted for all wavelengths up here for a preprocessed set of spectra. I've plotted the covariance for each wavelength with protein, and I've plotted the correlation, the blue curve, with protein. And you can see that covariance here in the visible range is quite high compared to in the near range. So here, this part will probably tend to dominate in a model that looks for covariance, while a model looking for correlation will tend to focus in this area where the blue values or the blue curve show higher values. So this is the difference between covariance and correlation. And the four methods we're going to investigate here is PLS, MPLS. They're both linear. It's local. It can handle nonlinearities by making locally linear models. And ANN, that is a true non-linear model. And in FossCalibrator, you can simply pick which one you would like to go with. This also makes it very easy to benchmark. First, to do an ANN, then we benchmark to a PLS model, for instance, and see how they perform side. The PLS regression method expands the univariate approach. So instead of just one item here, one part here, we add for all wavelengths. a multiplication, and we add all these parts. So the protein is equal to a regression coefficient number 1 multiplied by the intensity at wavelength, the first wavelength, 400 nanometers, plus number 2 times the intensity at 401 nanometers, and so on until we reach 2,500 nanometers, plus an offset and plus noise. And we would like to minimize the noise as we do in least squares solutions. Again, the idea is that during calibration, we estimate these coefficients. In this case, 2,101 regression coefficients. And when we have estimated these, we can use the equation on new unknown samples, but simply by multiplying the intensities measured, B1 times the absorbance or reflectance at 400 nanometers, and so on up to 2,500 plus B0, and then we have an estimate of the protein content. Behind the scenes, there is a lot of complex equations to be solved in PLS. And I would recommend you to look into the original literature on these things. For instance, the paper by Volt, Martens and Volt, or the paper by Martin Anderson here that describes 9 ways of doing PLS algorithms. This is one way to do it. And what I would like to highlight here is just that we do a lot of least squares solutions here. So that's why we have the partial least squares algorithm, that all these parts are, we're using the standard minimizing the least squares solution. As discussed, PLS is based on covariance. So the first thing we do in PLS is to multiply the spectra, the X, in this case X transposed, by the reference value, the protein. And this is a covariance way of doing it. It's X times Y, as we saw in the covariance equation. Sometimes this is good if we have large variations that are relevant to the constituent of interest. But sometimes it's not the best thing to do. Then we can try the MPLS method, because this is based on correlation between the spectra and the reference values. And instead of focusing on large variation in X, we focus on variation or correlation between X and Y. So small variations in X that correlate a lot with the protein content, they will come out in the first factors we calculate in the PLS model. So this will bring in these regions of interest in a more efficient way. So what we say is that PLS tends to bring regions of high variability into the model, while MPLS first brings regions of high correlation into the model. So it's for sure worthwhile trying MPLS, specifically if you have small peaks for a given constituent. It can be easier to catch these variations by the MPLS method. And we for sure recommend to try this method if you work with the wavelength ranges up to 2,500 nanometers. I have an example down to the right here from a compound feed spectral sample set. And you can see the visible part in this case have a quite high variation. These are pre-processed spectra, high variation. And this high variation will give a high covariance in itself. It might not be very relevant for protein, but it will give a high covariance. This range that might be relevant for protein or other components has a small variation, but the correlation to the parameter of interest might be much higher. So the MPLS will bring this part in before it brings this one in. PLS and MPLS are linear models, and they are very good for smaller databases with the low diversity. What we often have is actually quite large databases, and in large databases we have to handle many variations, and we can handle them in one model. If we can do that, it would be nice. We see nonlinear relations because of large concentration ranges. We see nonlinear relations because of temperature differences, both environmental and laboratory or production temperatures. We see regional and differences in the product type. We see seasonal effects. Milk in the winter and the summer are not completely the same. We see spectroscopic scatter. when we analyze solid samples that impact in a nonlinear way the signals. And we see many clusters in data if we have a large database. So all in all, we have this complex situation with complex matrices that calls for nonlinear models. And one way of handling nonlinearity is to make local models, local linear models. In this case, I have a very simple nonlinear curve here with two variables, just to illustrate it. And the local method would, in this case, for instance, partition this data set into 4 areas. So if we have a new unknown sample coming in here, for instance, then it would look in the surrounding and pick these samples to calculate a model for. And then it will make a linear PLS model in this range here. And then we will use the prediction from that model to tell what the protein content is. A new sample coming in up here would use samples in this surrounding to make a linear model here, and then use the prediction from that model. So the principle in local is that we have a spectral library. We have a lot of calibration samples where we have spectra and reference values. Let's say we have 2,000 samples in the spectral library. Then we will come in with a new unknown sample where we only have the spectrum. And then we will do a library search in the spectra and find 100, for instance, spectra that are most similar to the unknown spectrum. And then we'll take out these 100 samples and make a PLS model on the fly. So we make a custom PLS model for this sample, specifically this sample, based on the 100 samples that we take out. There are different settings that are of relevance here. You can set in the program a minimum number and a maximum number of samples you want to extract from the database. So you can say that I want at least 50 and I want a maximum of 200. And then it will search in that range. And the search is conducted by a correlation of the unknown spectrum to the spectra in the sample library. And when you have taken out the 100 sample of interest, we will make a custom PLS model that will be able to predict the protein content of the new sample. And built into this model, we have automatic outlier elimination, because since we don't have any human interaction here, it's completely done by the computer and the program. We have to make sure that outliers are eliminated in order not to impact the specific PLS model. And there are also specific things that you can set in the program with respect to the PLS model. It's the number of factors, minimum, maximum, and the outlier limits. So local, here are the settings you can see in FossCalibrator. Minimum, maximum number of samples, minimum, maximum number of factors. And if you want to use the outlier elimination, and we recommend that, so this is the default setting. Local handles nonlinearities by making a linear model in a small part of the sample space. A true nonlinear model is based on neural networks. And they were originally developed by inspiration by how the human brain works and the neurons in the human, the neural network in the human brain. And you can see in the human brain, we have a lot of neurons, 10 to the power of 12. We have a lot of connectivity among the neurons. So these network models that we have implemented are not quite similar to these in the human brain, but they're very useful for what we're going to use them for. The model of a biological neuron was developed already back in 1943. It collects a lot of input and makes a summation of this input, and then it adds it to a nonlinear transfer function, and then we get an output. So this is sort of what we call a neuron in the mathematical world of neural networks. The neural networks that we have implemented in FossCalibrator, they have an architecture. Sorry, I'll come to the architecture right after this, but they are utilizing the hyperbolic tangent sigmoid transfer function to introduce the nonlinearity, or to handle the nonlinearity. We can see that this function is quite linear in the middle here, and it has some nonlinear curvature up here and down here. So it can handle and cope with both linear and nonlinear aspects of the database. And the architecture that we have built this transfer function into looks like this. We have some input, which are the NIR spectra. We have some hidden layers here, the neurons with the nonlinear transfer function. In this case, we have 3 hidden neurons in the hidden layer. And then the output from these 3 hidden neurons, they are summed up and sent through a linear transfer function at the end, with the hope that we get a good estimate of the protein concentration. So we submit NIR spectra over here into the system, and then we get protein out to the right. The tricky part in neural networks is to estimate the W's, all the weights here. And the W's in neural networks, they can be compared to the regression coefficients in PLS. It's something that we have to estimate. In PLS, we can estimate them directly from the data. This is not possible in neural networks. Here we have to search for the best optimum or the best values of the weights. So the way we do this is that we submit data, we enter some random values, which might seem a little strange, but we enter random values for the weights because we don't know them. And then we submit spectra to the system, and we get protein content out here. The protein values that we get, we compare with the reference values, and they are probably quite far away. So then we use what is called backpropagation to train the network and to get a better estimate of the W's. And when we have trained the network, we can submit spectra and see how are we getting closer to the protein. And then submit back through backpropagation, predict, and go back and forth many times until we have a convergence of the system and the weights will not change anymore. Then we have a system that is stable and that is able to predict the protein concentration. Due to this randomness of the weights, we calculate several times with different random weights. This is what is called seeds in the program. So we throw in a new set of weights here, and then we make the back and forth training and convergence of the network, and then we do it again to see that we have not hit a local minimum in the model. We want to make sure that we have a good model and that it's able to predict the protein content. One challenge in this network is that if we have analyzed on our NIR DS2500 system, we will get 4,200 measurements over the full spectrum. So each spectrum consists of 4,200 absorbance measures. And that's a lot to put into a neural network. It increases a lot the dimensionality of the network. So what we have done is to utilize the PLS as a pre-processing. If we make a PLS model on the data before we submit them to the neural network, we can use these score values. These can also be called pseudo concentrations for the samples here. So instead of 4,200 measurements here, we can boil this down to, in this case, 3. That's a little low, but we can boil it down to 20 or 30 of these score values here. So we use PLS as a pre-processing and compression technique, not for the modeling itself, but for compression. And in this case, we can simply insert the PLS scores into the network instead of the original data. So we first do a PLS, and then we submit the score values, 20 for instance, for all the samples, or for each sample, and then we calculate the weights based from these data. It dramatically reduces the number of parameters, weights in this case, to estimate. So it gives us much more robust models and much faster convergence of the models. If we compare the 4 methods that we have talked about so far, MPLS, PLS, local, and NIR, we will start here with the PLS. And as I've written here, it's pros primarily and maybe a few cons for the methods, because I really, I like all of the methods. So I think I can only see the pro part. But PLS, it's a linear method. It's very relevant for smaller databases, less than 1,000 samples. It works fine with 50, 100, 200 samples. It works fine with if there's a low diversity of the database. And we recommend it for solutions based on transmittance, where you analyze a large part of the sample in the process. They are linear, and a linear model is preferred to a complex nonlinear model if performance is approximately the same. And just as a side comment here, on all our FTIR platforms, PLS is the only method that we actually use here. NPLS resembles PLS, except from the fact that it's based on correlation. It's also useful for smaller databases with low diversity. And then we recommend it and to evaluate it for solutions where we use reflectance as the sample presentation. It's very good for these minor components and to take out small variations based on correlation. And of course, the same comment with respect to robustness holds for the NPLS. ANN, the artificial neural networks, that's a true nonlinear model. It's relevant for larger databases where we have at least 1,000 samples, and it's not so useful because it's difficult to make it converge in smaller sample sets. It works very good with high diversity databases, also with low diversity databases, and it's good for reducing the number of models to maintain. And we use it for all our solutions. And of course, one of the main points is that it often gives a very good performance. And finally, we have the non-parametric method local, where we do these locally linear developed models, and we make one new model for each new sample. It's also most relevant for larger databases. If you use it on small databases, it will more or less compare to doing a full PLS on the full database. The drawback of local is the poor traceability, and also that repeatability is often jeopardized if you compare it to PLS or ANN. And this is due to this situation where you, with a new measurement, get a number of specific samples. If you analyze the same sample again, you may get a slightly different selection of samples and a different PLS model, which will add to the larger repeatability. It's easy to update. You can just add samples to the database, and the impact of outliers, it's not that high because the outliers are normally not selected in the local process. Another way of showing these models is in this way, where we have 4 categories: the linear, non-linear versus parametric and non-parametric. And if we start with PLS and NPLS, they are linear models. They have fixed coefficients. We know the regression coefficients up front for unknown samples. So we call these methods parametric. The ANN is also a parametric model. We have a fixed set of coefficients that we can use when we have trained the model, and it's a truly non-linear model. The local is a linear model. It handles nonlinearities by focusing on small sample sets in the database. And it's non-parametric, because for an unknown sample, we don't know upfront how the regression will look like, since we calculate it on the fly. So we call this a non-parametric model. In FOSS, we have more than 500 commercial models within the near-infrared area. And within the near-infrared area, if my computer will change here. The near-infrared area, we use for approximately 75% of these 500 models, we use neural networks as the model type. And for the remaining 25%, we use PLS or NPLS models. Then we very often get the question, why don't you have a nonlinear, non-parametric model? And examples of these are support vector machines, Gaussian process regression, and other very interesting methods. And we are for sure investigating types like this. We have an example where we have investigated all these methods down here. And so we continuously monitor new methods out there. What's important to us is that the methods that we implement in FossCalibrator, they do a robust job over time on many data sets. And many of the investigations conducted with such methods here are on 1 or 2 or 3 data sets where they make a difference. But if you take in another 10 data sets, then it's a little bit doubtful sometimes if it will also be a better method on these data sets. So we would like, on average, that it does a better job compared to what we already have. And this is also the background for FossCalibrator, where we have implemented PLS, MPLS, ANN, and local. And the first ones here, they are based on templates. So if you know the instrument type and you know the product type, a template is implemented, and you can simply go through this using our template and make a model on what we use as the optimal settings for this specific data set for this specific instrument. There is the thing called the no free lunch theorem. Averaged over all possible data generating distributions, and that's many, every classification algorithm has the same error rate when classifying previously unobserved points. In other words, in some sense, no machine learning algorithm is universally better than another. And that's why it's good to be a data scientist, but it also gives a lot of problems, of course, because you have to benchmark all the time. But what is important here, as I said, is that if we know the data, we know it's near-infrared data, we know it's from 1100 to 2500 nanometers, we know its reflectance, and we know we have a database of 10,000, for instance, then we have the template to do this the best possible way. And this can guide in helping selecting the most relevant algorithms. And this is exactly the way we have implemented this in FossCalibrator. And my good colleague will now take you to FossCalibrator and give you a demonstration of how PLS and ANN can be used for developing application models. Thank you.
Hello and welcome to this FossCalibrator tutorial. My name is Thomas Nilsson and I'm a calibration specialist at Foss. In this tutorial, I will show you how to develop an ANN calibration. I will also benchmark it against PLS and show the impact of the database size on performance. The data used will be from an Infratech instrument. The product is corn or maize with an extended range of the moisture content from 4 to 53%. Let's start a project and call it corn ANN. Instrument is Infratech and the product is corn. We start create. Now we should import our data file. Called Infratech corn moisture. And we will keep this split time based with the same default values. Choose moisture. And now we can evaluate the data based on PCA and PLS. That is, looking for potential spectral and reference outliers. As mentioned in the previous session, we should be aware of cleaning out data that ANN could possibly handle simply because of non-linearity effects. So let's start with the PCA to see if we have spectral outliers. And we can do that either from here, from this sample set overview, or from parameter details. Let's go to parameter details. Click all and press PCA. We can notice that we have a little bit spread in the scores. And for example, we have a few very high global H. Now we don't know exactly what that means. If these are some of the samples with a very high moisture content. So I will actually keep these for the time being. Let's do a PLS. It does not seem to be so many reference outliers, and linearity is quite okay actually. As we can see, there are some samples with very high global age and possibly some reference outliers, but since I have not evaluated individual sample sets that has been used to build up this total data set of 3,000 samples, I would not exclude any at this point. So we will move on to the model page and start creating models. The first model will be to use the recommended settings, which is a PLS model with the inverse MSC and no derivative as pretreatment. Then we can use this result as a benchmark when trying to develop ANN calibrations. So click OK. So you can see we have an RM-SCP value of about 1, slightly over. So that will be our target to see if ANN can beat that. So now we go to New, select ANN, and the parameter. Use the same data sets. For cross-validation, we can use random. Let's take 4 blocks. For optimization, different settings might be necessary to test, for example, continuous blocks and Venetian blind. But let's use this now. Complexity, you have a lot of settings you can do here. The wider range you set, the longer it will take to calculate. But it's another thing that you need to be aware of also, and that is that the number of weights should not be too high in relation to the number of samples you have and the complexity you have in your data. So for example, we have 3,000 samples. It means we should not have more weights than 300. So 300 times 10 becomes 3,000. So that's sort of a rule of thumb. So, and how to calculate the number of weights? That's the number of inputs times the number of hidden, plus number of hidden times the output, which is 1, plus 2. And in our case, we could potentially use 28 inputs and 10 hiddens and end up in 292 weights. But that will probably be too much. Let's go for a somewhat more modest setup and select 20 to 25 inputs with step 1, and then 3 to 6 hidden neurons, and maximum number of seeds 5. Regarding pretreatment, I will start with no scatter correction and no derivative applied, since that is the most common setup. So this is just left from the PLS default setting. So I will actually remove that and no derivative. Okay, now we can start creating our models, and that will take some time. Now it has completed, and we can see that the RM-SEP for validation is slightly better for the ANN compared to PLS. So some 0.88 compared to 1.03, a difference of 0.15. In the information box, we can see that the number of factors used is 20 inputs and 6 hidden. So that was the optimized model that FossCalibrator has selected or found. If we look on the 2 graphs, we can have them side by side. We can still see that the ANN performs quite well compared to PLS. It's more struggling in the high region, even though a lot of samples are well performing. Remember that I choose not to use scatter correction. Let's see if my assumption based on previous experience was right for this data. In order to make it a quicker assessment, I will only create one architecture, the 26, but still with 5 seeds. So let's go to New, select ANN and Moisture, Same here. Select 4 blocks, and in complexity we use 20 and 6 hidden, and maximum number of seeds 5. And actually this is the default coming up here, so it's not the last setting I use for ANN, so that's fine. And then we can start a new model. That will not take as long as the previous run. And now it's done, and we can see that the RMSEP for the validation set is actually slightly higher using scatter correction compared to without. So it means my assumption was right, that scatter correction for transmittance data using ANN does not always help, and certainly not in this case. Okay, coming back to the comparison between ANN and PLS, you may think it's not a very significant improvement using ANN compared to PLS, at least not based on the data that we've used here. I need to emphasize that the data we have used in this tutorial has been manipulated for the purpose of training only, so it should not be used for any other purposes. And this is quite clear if I compare with the official model of the latest version. Then we actually have an RMSEP for the validation set of 0.51, as we see here. Why don't we get that with the ANN model? Well, first of all, it's difficult to compare different validation sets. So let's import the validation set used for that model and see how our PLS and ANN models developed here in FossCalibrator compares. So we go back to samples, import, and use that for validation only. Then we'll go back to models and predict, select moisture, statistics, deselect here, take imported sets and this test set used for the official calibration, COMA26. Then we update, and then we can see here that our best ANN, the first one, has an RMSEP of 0.72 roughly, and the PLS is 0.94. Still a difference between ANN and PLS, maybe a little bit more even now, but we are still a little bit worse on the ANN model compared to the official model. So why do we get so much better with the official model, like 0.51, compared to what we get here? Well, it's all in the data. The data used for developing COMA26, the official model, is substantially larger than the 3000 dataset we have used here, where only about 2000 samples were used for training. The database for the official model comprises more than 9,000 samples with a lot more variability than we have in our demo set. In addition, it's also sharper due to the manipulation of the demo data. In order to illustrate this, let's import the data and make a run with the same architecture as for the official model, which is 25. As mentioned in the previous session, we use 3 sets in the MATLAB software tool, hence we will combine the calibration and the stop set into one training set and use the test set for validation. So let's make a new project, call it like that, Infratech, corn. Calibration set for training. stop set for training as well. And the test set for validation. So as you can see, we have 9,000 samples for the training set and about 1,700 for validation. So now we go directly to models. Let's do a PLS calibration just to have something to compare against. Skip the outlier model now. Click OK. While that's going, we can start our ANN. So that's fine. Let's do 4 groups and (25) with 5. And we skip scatter correction and click create. So the PLS is done, and we can see that we have 0.81 as the RM-SEP for the validation set. It has completed, and we can see that we get a fantastic RM-SEP of 0.47, which is even better than the 0.51 we got with the CORMA 26 official model. If we click and look at the graphs on these two models, we can see that we get a really good, especially in the upper region where PLS can't really cope, and also some samples here that falls out completely. This illustrates that ANN with this type of extended range data really can do the job and get a RM-SEP of almost half the value of what PLS can do. So that was all for this tutorial.